So good morning. We will start our discussion. Can you see the notes? Can somebody confirm, please?
Yes, sir.
Okay, good. So till now, in discretization, we have studied the finite difference method, and we have seen an example of how to use the finite difference method, and any other examples you can deal with the same way. Because ultimately you have a certain number of derivatives, first order or second order or mixed second order, and then you have to reduce the derivative into an algebraic form by using Taylor series expansion. So you can apply that method to any sort of equation, any sort of partial differential equation. Okay, and so after that we have seen how to solve the equation when there is variation with time, and we have seen that based on the scheme for variation with time, we can either have a scheme which is known as explicit scheme, in which case the new properties which are calculated are based only on the previous time step properties, and we have also seen that we can have an implicit scheme where the new properties which are calculated are also calculated taking into account the new time step values. So as a result, what happens, we have to solve a set of simultaneous equations for any implicit scheme, whether it is fully implicit, partially implicit, semi-implicit, like Crank-Nicolson scheme. There we have to solve a set of simultaneously solve a set of algebraic equations. The number of equations depend on the number of nodes or grid points that are used. And for explicit scheme, we can directly solve each equation and get the value of a parameter, say temperature or velocity, at each grid point on node separately. And this is only valid obviously for time dependent problem or unsteady problem. For steady state, you anyway have to solve a set of equations to get the values, because for each point the values depend on all the neighboring points. And we have seen the individual say for each process, explicit and implicit, what are the advantages and disadvantages. Okay. So what we are going to do is we are going to have a very brief discussion on stability and error propagation. So this is only, say, for this course, this part is only very briefly there in the syllabus. In general, it can be an entire course itself, stability and error propagation. But for our case, we will just want to know what are the different types of errors, and based on that, whether there is any consequence of any of the schemes, whether a scheme is suitable for all conditions or not, based on the errors, how the errors, whether the errors are increasing or decreasing. Based on that, we can define whether a scheme is stable or unstable. So these things we will see, and then we will go into the next chapter, which is finite volume method. And for the rest of the course, from today onward, we will be discussing different aspects of finite volume method, starting from very simple aspects and gradually going into more and more into more complex aspects. And you have to solve the programming assignment. So one assignment I have already given. I have not formally given it, but we have discussed in the previous class. So start working on that. If you can finish it quickly, it's better. If you keep it for the last moment, then it becomes hectic, depending on the situation. And for finite volume method also, I will give programming assignments. There are not many numerical assignments which you can solve by hand calculation. So I'm not giving any numerical assignment, because all these CFD type of courses depend on actually solving or rewriting programs. Okay. So artificially I can create a problem which you can solve by hand, but that way you cannot learn CFD in a very good way. Obviously I have to do that for the exam, but you can expect many questions which are more like theoretical type of questions in the exam, unlike other courses like say gas turbine, where we have much more numerical problems. So anyway, let us continue. And for the theoretical part, you have to study the notes vigorously. That should give you a very good idea. And from the finite volume part, starting from the finite volume part, which we are starting today, you can go through the book of Patankar, which we will be closely following for the rest of the course until towards the end, where we will go into some more complex things which are not there in the book. I hope I am audible. Can somebody still confirm once more?
Yes, sir.
Yes, sir.
Okay, good. So now what are the different sources of error? Okay, let us try to understand. When we are solving a numerical problem, okay, first let us define what is the stability of a scheme. Okay, so a scheme like say explicit scheme or implicit scheme. So these are schemes, right? So a scheme is called as stable if for each step in calculation, like you are going through different time steps, right? Or you are going through different iterations. So for each step, the errors are not increasing. Okay. So for example, if the errors in this time step for each point, okay, for each point there are say 100 points. I have divided the domain into 100 points. So the error when we calculate or when we solve a problem, we consider the highest error. So for each point there will be some error, right? How do we calculate error? By the way, we compare the error with the. So we basically compare the value at each time step with the previous value, because you do not know the correct value, because otherwise we would not have solved the problem if we had known the correct value, right? So because we do not know the correct value, we are trying to what we do is we compare the previous time step or iteration value to the previous iteration value to the current iteration value, and see what is the change that is occurring. So if the change is not much from one iteration to next iteration, we say that we are going towards the correct result. Okay. If the change keeps on increasing, okay, so this change we have to calculate for each point. So if I have divided the domain into 100 points, we have to calculate the change for each of the 100 points. So, and we have to find what is the maximum value. Okay, so that is the maximum error in each say step, okay, or in each iteration. So if we see that the error is increasing, okay, with time, then the scheme is not stable, because what will happen after a few iterations or after a few steps, the error will become too large, okay, and your solution will, this is known as divergence. So solution will diverge, okay, it will go towards the wrong solution, or it will just blow up, means you will get infinite temperature or something like that. On the other hand, if the error is decreasing with each iteration or each step, okay, we see that we say that the scheme is stable, and we are going towards the correct solution. Okay. So now what do we mean by error? Okay, stability now we have understood in terms of error. If error increases, scheme is unstable. If errors do not increase or decreases, scheme is stable. Okay. Ideally errors should decrease. Okay. If it remains similar order, then it is actually just on the boundary of stability. So you will not be able to reach the correct solution, because you always have the same error. So errors should decrease with each iteration. Okay. So now there are two sources of error in a numerical simulation. Okay. One is known as discretization error, which is also called as truncation error, and second is known as round off error. Okay. Let us just have a quick discussion on each type of error. So this discretization error is the error which is induced when you approximate the say analytical solution. So you have a say analytical solution or a correct exact solution, okay, mathematical solution, but we cannot capture that exact solution. Why we cannot capture? Because while numerically while getting the solution, we have approximated the derivatives by writing them in terms of differences using Taylor series expansion, and as a result we have truncated some terms there, okay. Similar type of errors will also be there in other schemes where we do not use Taylor series expansion, but similar errors will still be there. Okay. So basically we have ignored some of the higher order terms, and as a result there is a certain error because of this. Okay. This error is known as truncation error or discretization error. How can we reduce this truncation or discretization error?
By using higher order schemes.
Correct, by using higher order schemes. What can be another way?
Sir, decreasing the delta x part.
Correct, good. Decreasing delta x or delta t. Okay, whatever is the means decreasing the step size. So because it is proportional to the step size or proportional to the square of the step size, depending on the order of the equation or order of the method which we are using. So this is unavoidable in discretization. Okay. Obviously, we can improve as you have already said correctly that either we can use higher order schemes or we can use lesser delta x value or delta t value. In both these cases, you will need more time to solve the problem. So there we have to go to a compromise. Either we want to solve the problem quickly, but we have slightly more error, or we want to take more time but get much more accurate results. Okay. So the second error which is induced is known as round off error. Okay. This occurs, everybody knows what is rounding of a number. So when you are calculating a number using a computer or a calculator, you can only store the number up to a finite number of, because you are using a finite memory for storing a number, you can only store it up to finite number of digits. Okay. So for example, 8 digits or 16 digits, something like that. So if I use a very crude say analogy, so if I have a say number 1 by 3, and if I only store till 2 digits after decimal, it is 0.33. If I store till 4 digits after decimal, it is 0.3333. Obviously, the second case is much more accurate as compared to the first case where there is a large error, right? So the computer typically stores it till say 8 places or 16 places. You can define, there is an inherent limit of the computer, each computing system up to what places it can store, but you can define the algorithm, or you can ask the program so that it can store till less number of digits also. So although inherently say computer can store till 16 digits in MATLAB, you can ask it to store till say 8 digits. Why? To save memory. Okay. So that you can store more numbers. Memory becomes a very important issue in CFD problems. You will understand later when you do practical problems. Say you have 1 billion points. Okay. If I have 1 billion points, it can easily happen in a 3D problem. I divide each side into 1000 points. So I will have 1000 into 1000 into 1000, 1 billion points. And for each point, I am storing certain number of data like temperature, velocity, u velocity, v velocity, w velocity, pressure. Okay. So ultimately, for each point, you need certain amount of memory. So say for 1 point, I need say 10 bytes of memory, or say 20 bytes of memory for storing all the data. Okay. So if I need 20 bytes of memory for storing all the data, so for 1 billion point, I need 20 billion bytes of memory for storing the data. Okay. So 20 billion byte means it is 20 gigabytes, 20 GB. Okay. So you need at least 20 GB RAM or more than 20 GB RAM to do the calculation. Otherwise, your calculation will not run because you are storing this in the accessible memory, which is the RAM, right? While doing the calculations. So memory becomes an important issue. So sometimes we have to compromise on the number of digits till which we can store. So anyway, that is another discussion. But what happens is that this error, which is very small, say up to, we are storing up to say 8 digits. So at the 8 digits, there is 8th digit, there is an error. So we are accurate up to the 8th decimal place. You can say that, sir, this is a very small number, 8 decimal place there is a inaccuracy. How will it matter in our calculation? We are not bothered with that. But what happens that you are solving for millions of steps, so what say if in each time step I am solving for 100 iterations, then if I have say 1 lakh time step, easily it can happen in any practical problem. Say I have 1 lakh time steps, so I have to solve for 100 iterations into 1 lakh time steps. So 10 million steps, 10 million iterations. Okay. So, and in each step again, there are a lot of calculations that are occurring step by step. So, what happens? These errors may build up. Okay. They may build up very quickly also, depending on the algorithm, and they may affect the correct solution. Okay. So, this also sometimes can become important. This is unavoidable, but this can be mitigated by using, or like you can reduce the effect by using proper algorithm. For example, I don't know whether, okay, let us just discuss. It's not directly related to your course, just let me give an example. So sometimes I have seen many students, when they are asked to write a program to find out whether two numbers have opposite sign. Okay, so there is a number A and a number B, and you want to find out the opposite sign. It may be for a different program, but part of the program is that you want to find out whether the two numbers are of opposite sign. What do you do generally? I have seen many students will write a line like this. If AB is less than 0, then basically whatever means, it means that they are of opposite sign. Because if they are of opposite sign, the product will be negative. A into B will be negative. Either A is negative, B is positive, or B is negative, A is positive. So they think that within one line we are able to give the condition to directly find out whether the means it's a clever solution. But actually it's the opposite way. This is not the proper way of finding whether two numbers are of opposite sign. The better way would be to individually find whether A is, so you have to write a statement like if A is less than 0, do this, whatever, and if B is less than 0, do this. So based on these two, then you have to find out whether they are of opposite sign or not. So basically you have to separately find out the sign. So you can say that, but that takes more number of steps instead of directly solving in the first case. Okay. So the first solution looks much more elegant. But what happens is that for the second solution, if you have say a round of error of say you are storing till say 8 digits. So your error, round of error for the second solution where you are individually checking will be at the 8 decimal place. So it will be of the order of 10 to the power minus 8. Okay. Whereas in the first case, what will happen when you are say multiplying two numbers till 8 decimal places? So your accuracy will actually reduce to 4 decimal places. Okay, drastically it will reduce. Why? Because the 4th decimal place, when multiplied by the 4th decimal place, in so for a number, the 4th decimal place, when it gets multiplied by the 4th decimal place in another number, it leads to the 8th decimal place. Okay, so if you multiply the 5th decimal place by the 5th decimal place in another number, it leads to the 10th decimal place. Okay, and that is all obviously ignored because we are rounding off at 8 digits. So our accuracy drastically reduces to only 4 decimal places just by that one step. Okay, so that is a very crude method of checking whether two numbers have opposite sign. We should never use that type of condition in our programs. Okay, although I have seen many students do like that. So anyway, that gives you an example how round off errors can build up, and they can build up quickly also. So, okay. So now discretization error is part of your algorithm, discretization method. What method you are using for discretization? Okay, which order you are using? Okay. So let us try to understand then how errors can increase. Okay. So when we are saying that errors will increase or error will not increase, we are talking about the second type of error. Okay. So to do this, let us consider a simple example. Okay. Del t is equal to alpha del square t del x square. This will be x instead of t. Okay. So del T del T is equal to alpha del square T del x square, which is our 1D heat conduction equation. So we know that we can discretize it in this form. Okay. This is the explicit method. You can use any other method. Okay. Ti k plus 1 minus Ti. So actually I will just show you the explicit scheme, because inherently the other schemes, any implicit scheme is stable. Okay. The problem of stability comes for explicit scheme. Okay. So that's why I am giving the example here. The explicit scheme is not always stable. Implicit schemes are always stable. So Tik plus 1 minus Tik. If you remember correctly, what does it mean? It means that for the ith point, so we have divided the domain into n number of points. Okay. Don't have it here. But we have divided the domain into n number of points, right? And have the 1D. Anyway, you remember, but for the sake of completeness, let me show. Okay. We have divided the domain into n number of points, and I is any general point, ith point. For the ith point, and k is the kth time step, k plus 1 is the k plus 1th time step. Okay. So Tik plus 1 minus Tik by delta t, this first order approximation, and for this second order approximation is alpha by delta x square Ti plus 1k minus 2 Tik plus Ti minus 1k. So in terms of previous time step values k and ith grid point value and these two neighboring grid point values, we can express this equation. This is known as the discretized equation, right? We have discussed in the previous class. Just hold on for a second. Okay, you can still hear me?
Yes, sir.
Yes, sir.
So this we already have, we have seen. This is the discretized equation. Okay, so this already has the first type of error. Okay, the discretization or truncation error. What is the order of this truncation error, which we have discussed in the previous class? What is the error in this discretized equation? Order of error.
Sir, delta x square comma delta t.
Correct. So it is delta x square in space because we are using second order scheme in space, and first order in time, delta t. So now let us consider A to be the analytical solution or exact solution of this PD, the first equation. Okay, for the PD, not the discretized equation. For the PD, say the exact solution can be obtained just by integrating, and that is denoted by A. Means T is equal to A for all points, and all points means A, basically there are different values of A for different I points. Okay. Then the exact solution for the difference equation, okay, for each difference equation, say the exact solution is D. Okay, it means that if we could have solved it without any round of error, if we could have solved this equation without any round of error, then we would have obtained the solution as D. And let n be the numerical solution, the solution that we will obtain by writing a program, okay, and solving it using any computer. This is the real solution using a real computer with finite accuracy. Okay, so the difference between D and N is the round of error. Okay, and difference between A and D is the truncation error. So let me just keep this open on this side for your reference. What is A, D, and N? So now, because the program is written to solve the difference equation, okay, discretized equation is also known as the difference equation. in this case because we are using the finite difference method. N must satisfy the difference equation. Okay. So n will satisfy this equation, right? So it means that Nik plus 1 minus Nik by delta t is equal to alpha by delta x square, Ni plus 1k minus 2 Nik plus Ni minus 1k, where n is the numerical solution for the corresponding points like ith point, I plus 1th point, I minus 1th point, k at time step, k plus 1 at time step. Numerical solution for temperature, which we are getting by solving, writing a program and solving it using a real computer. Now let this n, which is the numerical solution, is be equal to the exact solution of the discretized equation, okay, difference equation, plus round of error epsilon. Okay. So where epsilon is the round of error, obviously. So we can write this equation here as, so replace all the n values with d plus epsilon. So di k plus 1 plus epsilon I k plus 1 minus di k minus epsilon I k by delta t is equal to alpha by delta x square. So again for this di plus 1k plus epsilon I plus 1k for this term. Similarly, you can write the other two terms. So minus 2 nik will become minus 2 dik minus 2 epsilon ik, and plus ni minus 1k becomes di minus 1k and epsilon I minus 1k. Let this be equation 1. Okay. Now, as d is the exact solution of the difference equation, obviously d also has to satisfy this equation, difference equation. So this is the exact solution. So this has to satisfy. So which means that di k plus 1 minus dik by delta t is equal to alpha by delta x square, di plus 1k minus 2 dik plus di minus 1k. Okay, because it satisfies the difference equation. So from 1 and 2, if you subtract 2 from 1, you get an equation for the error. Okay, if you subtract 2 from 1, you get an equation for the error, which is epsilon I k plus 1 minus epsilon I k by delta t is equal to alpha epsilon I plus 1k minus 2 epsilon I k plus epsilon I minus 1k by delta x square. Okay, what are these terms? Epsilon I k plus 1 is the round of error for the ith grid point value at the k plus 1 at time step. Epsilon ik is the round of error for the ith grid point value at the kth time step. And similarly, this value epsilon I plus 1k is the I plus 1th grid point round of error for the kth time step, and this is epsilon I minus 1k is the I minus 1th grid point round of error for the kth time step. Okay. Or if you rearrange, you get epsilon I k plus 1 is equal to epsilon I k into alpha delta t by delta x square into whatever was there in the bracket, epsilon I plus 1k minus 2 epsilon I k plus epsilon I minus 1k. So for an explicit scheme, we have obtained an equation on how the errors propagate with each time step. Okay, so we can find based on the previous errors. Okay, so in this class in this course we will not go into further details. Okay, so this can be solved actually using Fourier series, sorry, and it can be found that this epsilon I k plus 1 is greater than epsilon I k. So what we want to find? Okay, so this equation is the equation for error propagation, and we want to see whether epsilon I k plus 1 is greater than epsilon I k or not. Greater in the sense that whether the absolute value is greater than or not. It can be positive or negative. Absolute value has to be less from the previous step so that the scheme is stable. Otherwise, it will not be stable, right? So the discretization scheme and the solution is stable if epsilon I k plus 1 by epsilon I k, the absolute value of that is less than equal to 1. Ideally, it should be less than 1. Equal to 1 is just at the limit of stability, which is not good because you will not be able to go to a correct solution. You will not blow up also the solution, but will just the error will remain similar. So we will not discuss that how it is derived, but it can be derived using stability analysis. That this value is less than 1. From this equation it can be derived that this is less than 1 if alpha delta t by delta x square, if this term is less than equal to half. Okay. So this actually gives us a condition for the explicit scheme which shows that you cannot have arbitrary values of delta t or delta x. Okay. Based on the value of delta x that we are taking. So if we take a certain value of delta x, we are dividing the domain into 100 steps, say, then the delta t should follow this condition. Okay. What is this condition? So say if the alpha is not changing, there is an upper limit on delta t for an explicit scheme. So delta t is proportional to delta x square basically. Okay. Delta t is less than equal to half delta x square by alpha. Okay. So delta t is proportional to delta x square. So if I have say 100 grid points and my scheme is working with 0.1 second time step, if I increase the number of grid points to 200 grid points, what should be my time step? If for 100 grid points I have 0.1 second time step. If I increase it to 200 grid points, what should be my time step? Very easy question. Just Dushyant, what will be the time step?
Sir,
Cannot hear anything.
hello, sir.
Yes. What will be the time step value? You are not listening, huh?
Sir,
Kashif?
for 200 grid point,
Yes.
it will
Dushyant.
also, sir, 0.1 second. We are not increasing delta x.
Why we are not increasing delta x? It's not, answer is not correct. Kashif?
Sir, is it 0.4 seconds?
No. Why will it be 0.4 second?
Maintain delta t by delta x square is same.
Delta t is proportional to delta x square.
Yes, sir. In that way, getting t equals 0.4 seconds.
Mayank? What will be the correct answer?
Sir, can you repeat that last question?
You are not listening. Question is, if I have 100 grid points, I have a domain, say I am solving a problem like I defined in the previous class, and I have 100 grid points, and for that explicit method is working with time step of 0.1 second. So now if I have 200 grid points, what should be my time step?
Sir, it will be cube of that.
It will be
Cube of
what cube of that? Not correct. Madhumita?
Sir, 0.2
second.
0.2 second. Excuse me, sir.
Yes.
Sir, actually, I am in quarantine, so I have to go now for medical checkup urgently. So I have to leave the class.
Okay. Okay. I will give you consider your attendance.
Okay, sir. Thank you, sir.
So correct answer is it will be 0.025 second. Okay. 0.025 second. Why? Because if you are increasing the number of grid points from 100 to 200 for the same distance, because your domain is same, your grid size is decreasing to half the value. So if the delta x previously was 2 mm, now it has become 1 mm because you have 200 points instead of 100 points. So grid size is decreasing to half the value. So the time step has to decrease by to 1/4 the value. Okay. Previously it was 0.1, now it will be 0.025, 0.1 by 4. So this is the upper limit. Okay. So we will stop for this part here, and we'll continue to the next chapter. Any questions? No questions. Okay. So the next part that we are going to start, from this part onward, you can follow the Patankar book. Okay, previous part better to follow the notes itself. Here also notes will be most suitable, but you can, if you want, you can follow the book by Patankar also. So we are going to see another method of discretization, which is known as finite volume method. Again, it will be very familiar to those. Everything is almost similar in this course curriculum as compared to the elective CFD course, except that here we have more time for more solving assignment problems or programs, do one programs, because it's a 4-credit course. But to those who are not who have not done any CFD course, it will be a new thing. Okay. So we have seen finite difference method. So some of the advantages we will discuss later anyway, but some of the advantages and disadvantages of finite difference method is that, say you have a domain which is very regular in shape, like a rectangular domain or a square domain or a cylindrical domain. So in that case, you can divide the domain into a certain number of points in a structured way. Means the points will be going from say this way. Okay. Like this, in a structured way, I can divide the domain. So in that case, then I can use Taylor series expansion and find out the approximation of all the derivatives. However, if my domain itself is irregular, okay, like this domain, so then if I want to exactly capture the boundary of the domain, at least for the boundary, near the boundary region, I cannot have this type of nice rectangular grids, right? And if I want internally also, we may not have nice rectangular grids like this. So because what happens in that situation, because you do not have nice rectangular grids like this, these I and j values are not, you cannot define in which direction I or j is increasing, because there is no I and j here. You cannot even say what is the neighboring point along the x direction and what is the neighboring point along y direction, because these are all arbitrary. Okay, all these points are arbitrary. So they are not in a single line. So in that case, we cannot use finite difference method, because we cannot write the derivatives obviously in terms of its x and y neighboring point. What option would be there to can it happen that we can still solve for a domain like this using finite difference method, or is it totally impossible? Can anybody explain?
It is
Say this
possible,
domain.
but
Yes.
but at the boundaries it is not possible.
Yes, and somebody else was also saying.
Sir, it is not possible. We have to first convert it in a regular region, then I think.
No, it is possible, but your answer is slightly correct. First answer also is slightly correct, means partially correct. It is possible, obviously, but what will happen is that this exact shape you will not capture. So what will happen is you will have, say this, say I have a region like this. Okay, so to capture this, you will have, actually second answer also is quite good. I will just explain once. So you will have grids like this. Okay, so you will have to approximate using grids like this, means using straight lines at the boundaries, and then you will divide into, say, grids like this. My drawing with mouse may not be accurate, but you will understand. So what will happen, you will have a staircase like effect, okay, for the curves. Now for solving, then you can envelop this entire thing like the second student was saying, and just then like you have, say, in this region, so this may be the curved object, and then I can only consider the grid points which are internal, and for the external grid points I I will also have to solve, but I can give some property values which do then makes the outside part not interact with the inner region. Okay, it's possible, but it will be inaccurate. Particularly, it will be inaccurate at calculating the boundary values like heat flux or shear stress. Okay, but still it's possible. Okay. So this is one drawback. But what is the advantage? Finite difference method is very easy to implement. Okay, it is very easy to implement, and for simple problem, simple means simple geometry. Many problems have simple geometry. Many real life problems like a square or cubic geometry we can approximate. Cylindrical geometry, circular, spherical, any regular geometry, finite difference is quite suitable. The advantage is that you can capture very complex physics. Any derivatives you can convert, right? So if I have a complex physics with lot of derivatives, mixed derivatives, it does not matter because we will be able to convert it to a difference equation like this. So any derivative we will be able to convert. So it is possible to capture complex physics using finite difference method, but it is difficult to capture complex geometry. Okay. So we'll take a look at another method which is very suitable for both simple and complex geometry. So this is used very widely used. This is the most popular method for discretization and is used in many commercial software. Even when we are writing our own codes, this is very widely used. Okay. And there are other advantages. Okay, I will just explain in a minute what are the other advantages. So this method is known as finite volume method or FVM. Okay. Remember that there can be other methods of discretization also like FEM, okay, finite element method, but that is not widely used for CFD problems because it takes more time to solve. Means for the same problem, the simulations will take more time to solve. So it is FEM is not as suitable as a finite difference or finite volume method. FEM is more suitable for structural problems. But all these are methods of discretization. Okay. Sometimes people just equate CFD and FEM on the same level, but it is not true. CFD is a numerical, say it encompasses any numerical solution of thermal and fluid flow problem, and this FEM is just a discretization method. Okay. So anyway,
Sir,
yes.
sir, what are the drawbacks of FEM method? Means why we can't use that method?
It takes more time to means say if you want to run a simulation using FBM, if it takes 5 days to run, FEM method may take 10 days to run. Okay, it's not very suitable. We may still use it or prefer it when there is both structure and fluid flow problem. Means there is structure fluid interaction, like say flow air is coming from one side and hitting a surface, and because of this the surface is bending. So now you have to calculate the flow of air also, and you have to calculate the bending of the surface also, means bending of the say structure also. In that case, because there is a structural part of the problem, FEM is much more suitable. But for normal problems, we do not we do not use it because it is numerically more expensive. Okay, numerically expensive means takes more time to solve with the same accuracy. So finite volume method, what is it? Let us define. Anyway, we will be reading this because it's there in the notes, but just for let me give a formal introduction. It uses integral form of conservation equations. So at this point, these statements may not be clear, but once we go through an example, it will be clear. Okay, what these statements mean. So it uses integral form of conservation equation. Okay. So when we convert the PD, partial differential equation, into a discretized equation, we do it by integrating the equation over the entire domain or subdomains. Okay, so that is what I mean by using integral form of conservation equation. For doing that, what we do is we If we could have integrated this equation over the entire domain, would we need any CFD to solve the problem? So if we can integrate the entire equation over the entire domain, do we need CFD to solve the problem? Or do we need finite volume method or any other method to solve the problem? I'm waiting for answers.
No need, sir.
No need, because anyway by directly solving, we are getting the analytical solution which will be exactly correct, right? So we do not need. So only in case where we are unable to solve for the entire domain, unable to integrate, then we have to use this type of method. So now when we are saying that we will still integrate the equation, it means that we will not be integrating it over the entire domain. We will divide the domain into some subdomains, okay, smaller regions. Why we will divide it into smaller regions? Because then we can use some approximation for doing this integration. Okay, for the larger domain, if we had to use the approximation, it will be very inaccurate. But if you divide into many small parts, say 1,000 small parts, then the approximations become quite accurate. Okay, that's why we will divide the domain into a number of subdomains. These subdomains are called as control volumes. Okay, we will divide it into a finite number of control volumes. Obviously, we cannot work with infinite numbers. It will take infinite time and infinite space to solve, memory to solve, infinite memory. So we will divide it into a finite number of control volumes. So each of these you see, so this is the domain, this pink line, okay, and each of these blue areas is the subdomain, which is called as control volume or a finite volume method. Each control volume is typically, so each control volume is represented by a point. Okay, so the value at each control volume is represented by a point. Typically, this point is at the centroid of the control volume. Okay, centroid of the control volume, or centroid means center of the control volume. So if I have a line, if it is a 1D problem, if I have a line, I have the grid point at the center of that line. If I have a square control volume, it is the center of the square. Okay, but for complex like pentagon, it is the centroid of the pentagon. Okay. These control volumes can be of arbitrary shape. It can be pentagon, hexagon, triangle, whatever. Okay, it does not matter. I can have few pentagons, few hexagons, few triangles, few squares, few quadrilaterals. Anything is possible. Okay, so this grid point represents the value of all the variables. These values are only stored at the center. It means, so for example, if I have temperature and u velocity and v velocity for this 2D problem, I will be storing them at this point. Okay, so you cannot say what is the value at other point in the subdomain. So if I hope you can see, say, let us take another color. So you cannot say what is the value here. Okay, because we are not storing the value there. You cannot say what is the value here also or here also. The only point where we know the exact value is, or we know the value is at the grid point. Okay. Similarly, for the neighboring control volume, we know the value here. For this here. Okay. So when we plot the values, we just plot these values, and then we have to interpolate in between to plot it nicely. Otherwise, we have. Remember, any numerical method gives us discrete solution, not a continuous solution, right? So we have solution at this point, this point, this point. You can increase the frequency, you can have large number of points, but still it will be at discrete points. Okay. So properties such as T, P, etc. are defined at these grid points, as I have explained. Okay. Any questions? Let us try to understand it better. Okay, so general 1D diffusion equation with source. Okay, let us consider d dx gamma d phi dx plus s equal to 0. This is like the heat conduction equation, d dx gamma d phi dx plus s equal to 0, as gamma is the diffusivity Phi is the variable of interest. It can be temperature or velocity or whatever. S is the source term. So what we do is, for any control volume, say this control volume or any control volume, we integrate this governing equation for the entire control volume. Okay. So over the control volume delta V, over the volume delta V, we will integrate d dx of gamma d phi dx dV plus the second term integral of S dV over the entire control volume. Okay. So basically our basically this is the conservation of the property for this control volume. Okay. So then because remember these governing equations are derived based on conservation equations. Okay. So for say this type of simple geometry, not this complicated geometry, simple geometry you can better understand. Okay. So say I have a control volume, this control volume which is shown by the hashed line. Okay. And it is represented by the grid point P at the center. Okay. So this is the pth control volume with the grid point P. Similarly, its neighbor to the right side, also known as east side, is E and represented by grid point E, capital E. And the neighbor to the left side, which is also known as the west side, is W, grid point W. Okay. And the boundaries or interfaces are represented by small e and small w. Okay. These are standard practice. So you should not use arbitrary terms like ABCD. Okay. So these are standard. So the grid point is denoted by P, east is E, west is W. Later we will see that top is north N and this will be south. Okay. So we can convert this volume integral into a surface integral by using divergence theorem. Okay. If you do not remember divergence theorem, you read it up. Okay. So basically it means that the flux, basically the conservation of flux in a control volume is governed by the amount of flux that is passing over the boundary. Okay. In physical term, it means that the flux is passing over the boundary, that changes the amount of flux that is present in a control volume. So this for this simple case, it will be gamma d phi dx E. Okay, this term gamma d phi dx at the east interface into the area A of this east interface minus gamma d phi dx at the west interface into the area of the west interface, because these are the only interfaces. It's a 1D problem. Okay, we are ignoring the other side. If it was a 2D problem, we also have to take these two into account. So 1D problem, we are just calculating the flux, and the flux is overall flux in the entire domain is gamma d phi dx into area at the east interface minus gamma d phi dx at the west interface into area of the west interface plus the source term. For the source term, we can integrate over the entire volume based on the average source. So if the average source over the entire volume is S bar into the area or the volume delta V. Okay. So this is equal to 0. So this is now this needs to be converted to some sort of equation where we represent this interface values, interface d phi dx E and d phi dx W, in terms of the grid point value E, P and W. Because remember, we are only storing the values at the grid point. We do not know what is the value at the interface. There is no value stored there. We only have, say, if it is temperature or if it is phi, we have phi capital E, phi capital P and phi capital W. We do not know what is the phi at east or small east, means east interface or west interface. So we have to approximate that. To do this, what is the next step? We assume something which is known as, profile assumption. Okay. We assume that the phi varies between neighboring grid points in a particular way. It can be linear, it can be quadratic, it can be cubic, it can be exponential, it can be logarithmic. Okay. It can be constant also. But we assume some variation between the neighboring grid points. Okay. And based on that assumption of the profile, we then calculate these derivatives at the east and west or whatever are the interfaces. Okay, so this part is known as profile assumption. How to take that profile assumption we will see later, but that is what is done. That is the crux of finite volume method. So there are two main steps. One is that you integrate the governing equation over each control volume. Three main steps: integrate the governing equation over each control volume, convert the volume integrals into surface integrals using divergence theorem, and then the derivatives that are present has to be converted to differences, or like basically they have to be written in terms of the grid point values using some profile variation, assumption of variation of the variable phi between neighboring grid points. Okay, so these are the main steps. Let me summarize. Divide the. So I will let us go through few examples. Then it will be more clear. Then you can ask questions. So divide the entire domain into a number of finite size subdomains. Okay, which are called as control volumes. Each subdomain is represented by a grid point. Integrate the governing differential equation over each subdomain. Okay. Consider a profile assumption for the dependent variable for evaluating the integrals to express the results. So first, consider a profile assumption for the dependent variable for evaluating the integrals to express the results in terms of algebraic quantities at the grid points. Means basically in terms of grid point values like phi p minus phi e or phi e minus phi p, like this, phi e minus phi p or something like that. So to do this, we need a variation of the dependent variable. Dependent variable is a phi, or say temperature or velocity, as a function of the independent variable. Here phi can only vary with x, but if it's a 2D problem, phi will be varying with x and y. So you need the variation with both respect to x and y. Okay. So these are the main steps in a finite volume method. Couple of important things to note here. The subdomains can be of any arbitrary shape. I have already discussed. It can be any shape. Okay. Towards the end of the course, we will discuss and we will see the derivations for arbitrary shapes. How to take into account arbitrary shapes in finite volume method. But for most of the course, we will be using regular shapes. But the discussions still hold true for arbitrary shapes also. It only the calculation becomes more complicated. Okay. Any complex shape can be tackled easily, unlike finite difference method. Okay. So with this also we have discussed. Let us go into another example. Okay, more detail. Let us consider steady state convection. Okay, let me take a break here because we have completed 1 hour. Let me take a break and then we will continue. Can you hear me?
Yes, sir.
Yes, sir.
You can see the screen also, right?
Yes, sir.
Okay. Just a second, please. All right. Let us continue. Okay. So we are discussing out finite volume method. Let us try to understand it in a better way. Okay. We'll consider the steady state convection diffusion equation with no source term. So if you remember the overall governing equation, generalized governing equation, we had four terms: del del t of rho phi plus del dot rho u phi plus del dot gamma del phi plus s. Okay. First term is the unsteady term. This we already know. I'm just repeating so that it is more ingrained in your memory. Second is the convective term. Third is the diffusive term, and this is the source term. So when we say steady state, it means that unsteady term is 0. And when we say that with no source, this term is 0. Okay, so it's just the convective term and diffusive term. So we want to solve this, okay, using finite volume. So for any control volume, it can be any arbitrary control volume like this or a nice regular control volume like this. We will have to, what is the first step? We have to integrate it over the control volume, right? So over the control volume, integration of del dot rho u phi minus del dot gamma del phi. Okay, del dot rho u phi. So within the bracket we can write del dot rho u phi minus gamma del phi dV over the internal control volume equal to 0. Okay. So basically this term is known as flux. Okay, it's the advective plus diffusive flux. So it is the, so gamma del phi is like minus k dt dx. Like in heat transfer you have minus k dt dx. Similarly here. So this is the diffusive flux, and this is like your convective or advective flux. Okay. This is denoted by J. It's a vector because it's had as a direction, flux as a direction, so J. So we can write basically this as del dot J, this term as del dot J. Okay, so integral of del dot J over the entire control volume we have to find. So what divergence theorem gives us is this integral, volume integral, is nothing but equal to this surface integral. Okay, del dot J dV over the entire control volume is equal to J dot N ds over the entire control surface. What does it mean? J is the same, J is the flux. Okay, dot N means in the normal direction at each place. So like say if this is the interface, so over the the flux along the normal direction to the interface over the entire interface. Okay, over the entire surface. So if this is the surface given by the dark line here, this is the surface. Over this entire surface, J dot N has to be integrated. Okay, this is the first step. So now in very complicated scenario, it may seem like very complicated, but for simple cases like this, we have very simple surfaces, so we can do that integration easily. Okay. For example, for this case, it is just there is no surface, means that this surface is basically it's a point. If it's a 1D problem, it's just a straight line. If it's a 2D problem, okay. Similarly, this surface. So if you know the flux at this point, you can easily find out the total flux over the entire surface. This flux minus this flux. Anyway, so let the grid point is at the center of the CV. As I have discussed, typically it is grid point is taken at the center of the CV, but it is not always true. There can be cases where it is taken at a different point also. Okay, but for this simple situation, let us think that it is at the center of the CV. So to calculate the flux across the control volume, to calculate this J dot N, okay, across the control surface, sorry, it has to be represented in terms of the variable value phi at the grid points. Okay, why? Because we do not know the value at the interface, and we cannot calculate the flux directly at the interface. So we have to resort to the grid point values. We have also discussed this, and we have also discussed that to do this, we need to assume how this phi varies from one grid point to another grid point. For example, linearly or quadratically, cubically, exponentially, logarithmically. So this is known as profile assumption. I will show you means continuation of this example later after this explanation. With suitable profile assumption, the flux can be written and integrated over the control surface to give algebraic equation in terms of phi at discrete grid points. Okay. So say this flux over this surface. Again, let me increase zoom. I can calculate the flux over this entire surface in terms of its area and individual flux by integrating over this surface. Similarly, over this surface, I can calculate the flux. Over this surface, I can calculate. So these fluxes will be in terms of grid point values. Okay, because we will take some assumption of how the variable varies between grid points, and then based on that, we will calculate the fluxes at the interfaces and multiply it by the area. This is the idea in finite volume method. That is what it means, this line. With suitable profile assumption, the flux can be written and integrated over the control surface to give algebraic equation in terms of phi at discrete grid points. Now, another major difference comes as compared to finite difference method. Okay, and this is one of the major advantage also. Okay, one was we have already discussed any complicated geometry, but this finite volume method, because we are using an integral form of the equation, we are basically integrating the equation over the entire control volume. So this discretization satisfies the principle of conservation over each control volume. Okay, because we are integrating the governing differential equation over each control volume, it satisfies the principle of conservation over each control volume, and as a result, it satisfies the principle of conservation over the entire domain also. Okay, why? Because as I have discussed, we are using integral form of the governing equation. Okay, if you use differential form of the governing equation like we do in the finite difference scheme, okay, still conservation is valid, but conservation is valid at infinitesimal locations. So each point it is valid. Okay, if you take any point, conservation will be valid. But overall in the volume, you cannot ensure conservation. Okay, but finite volume method directly, in principle, means directly, whatever is the discretization means however you discretize, it will ensure that conservation is valid over each control volume. Okay, this is another advantage. Why this becomes advantage? Because if you have a very crude coarse grid, if you have very less number of grid points, still the principle of conservation will be valid. Whereas if you have very coarse number of grid points in finite difference, there will be a lot of inaccuracy in the mass or momentum conservation or any other conservation, energy conservation. Let us continue with that discussion, means with that example. Okay, with another example, not that convective diffusion, but even more simpler example. This first example. Okay, d dx of k dt dx plus s equal to 0. Same example, but in terms of temperature and conductivity. So now it will become clear. So we are going through a lot of discussion vaguely, but we want to understand exactly what it means. Okay, how I am going to write the program, what it means. So say we have a 1D domain like this, like a rod or a bar or something like the wire. Okay, and you want to calculate the heat conduction. We have seen this case in the finite difference method also. Same thing here. Now what we will do? We will divide the domain into a finite number of control volumes. Okay. So say this is one control volume, this is second control volume, third control volume, fourth control volume, fifth control volume, sixth control volume. We have divided into 6 control volumes. Okay. Each of them is represented by a grid point at its center. Okay, centroid, here it is just the center of the line, because the control volume itself is a line. It's a 1D control volume. It does not have any area or volume. It has just a length. So, and at its center is the grid point. Similarly, so grid point 2, 3, 4, 5, 6, 7. We have 2 additional grid points and control volumes for the boundaries, okay, which we will see later how to treat them. But internally we are divided this. Okay. So take any general grid point and control volume. Let us take this control volume 5, okay, and the grid point 5. So this using nomenclature which is used in like many books, okay, which is the commonly used nomenclature, can be written like this. So this control volume goes from small w to small a, as I have explained here, okay, west interface to east interface, and is represented by the grid point P. So this is known as the pth control volume. Okay, this is very familiar to all the students who have taken CFD courses previously. For new students who have not taken CFD, this is new. For others, it's just a revision. We will have adjacent control volumes on both sides. Okay, so for example, for this 5 control volume, we will have the 6 control volumes. So that will go from say east to something like that. And similarly, we will have a control volume here, similar to this. Okay, I have not drawn it because for this it is not relevant. But this will be like this, and like this you continue. So this may be the 5th one, 6th one, 4th one. Okay. The length of the control volume is delta x, and the distance between adjacent grid points is delta xc on the east direction and delta xw on the west direction. Okay. So what our equation tells us, what our finite volume method tells us is that we have to integrate volume integral. Remember, so here the volume is just it's a one-dimensional volume. So going from west to east, d dx. So our equation basically we are integrating. Let me go to the equation itself. This is the equation, right? This we have to integrate over the entire control volume. Entire control volume is going from here to here. Okay. So going from here to here, we have to integrate. So integral of d dx k dt dx plus s from west to east. Okay. So west to east d dx k dt dx plus west to east s dx equal to 0. And we know that we can convert it using Divergence theorem to k dt dx. So basically the fluxes at these 2 points, k dt dx at east minus k dt dx at west, plus this integral is nothing but s into integral of dx from west to east, which is x at east minus x at west. Okay, so s into s is the, assuming we have constant s xc minus xw equal to 0. Okay. So generally all these x values, y values, these will be known once you have created the mesh. Means once you have created the control volumes, you are starting with a geometry, then you divide it into control volumes. This is known as mesh generation. So once you develop the mesh or grid, we have discussed in the beginning classes, you already know the location of all these grid points and all these interfaces in terms of coordinate values, basically numerical values of x, y, z. So these will be known values, okay, x, c, x, y. So now this question is how to evaluate this k dt dx at east minus k dt dx at west. And what we have discussed previously, that we need some profile assumption. What does it mean? Normal term. It means that how the t varies with x. How t varies with x between say here to here, and how t varies with x between here to here. If we can know that, we can calculate the derivative dt dx at this point and dt dx at this point. Okay. Obviously, we do not know that, so we have to assume. Okay. And we have to assume arbitrarily initially, and later we will understand that what we assume, if it is correct, means if it works, then it does not matter what type of variation we are taking. Ultimate solution will still be correct. Okay. Anyway, let us see some assumptions, profile assumptions. Up to this point, any confusion? Okay. Study this, and in the next class, if you have any difficulty, let me know. So first profile assumption we will consider is that the phi is constant, or in this case it is temperature, right? Temperature is constant in each control volume. Okay. So for example, here the temperature is, this is the temperature scale. So this is constant over the entire control volume going from west to east. Okay. So this is 300. In the next control volume, it is 295. In this control volume, it is say 280. Okay. So for each control volume, this is constant. Okay. So how will you calculate dt dx now at east and west? New students, those who have not done CFD. Can you answer? It's already written that we cannot calculate dt dx at the interface, okay, because of there it is not defined basically. There's a directly jump there, so we cannot calculate. So what is the conclusion? That this is not going to work. Okay, this assumption is useless. It is not going to work. Is it clear? Who are there?
Clear, sir.
Okay. Madhumita, clear?
Yes, sir.
Okay. So let us take a new assumption. Okay, what we will do is, we have seen constant does not work. So next simplest one is linearly varying. We'll assume that in each control volume it varies linearly. Okay, and grid point value is already fixed. Okay, grid point value is set again 300 whatever, 305 or like this. And based on the grid point value, there is a linear variation. Okay, within the control volume. So for W2E, it is like this. For E, the next control volume, it is like this. Is it going to work? Again, I am asking the new students. Old students already know this. Old means those who have done CFD course.
No, sir.
It is not
Yes.
going to work. Why yes?
So because we know the point that
So-
continuous, because it is continuous.
How will you calculate KDTDX? We can calculate obviously based on this line. I can calculate KDTDX at each point, right? So I will be able to calculate this KDTDX at each point based on the slope of this line. But for the next control volume, when I am doing the calculation, again I have to calculate the flux at the same point. Then I will be calculating based on this slope, right? KDTDX. So if K is same, you have two heat flux, means this value is different, very different from this value. Can this happen in a physical problem? Can the heat flux change?
Yes, sir, I understand that slope is different.
Correct.
Slope
So
is-
that's why this is also not possible. Okay, KDTDX is not continuous at the interface. As heat flux is not equal on both sides of the interface, this assumption is not acceptable. Okay. So then we will take another assumption. Again, linear variation, but variation between the grid points. Okay. So from P to E, we have a straight line. From W to P, we have a straight line. But within the control volume, it is not continuous. Means it is continuous, but it is not a straight line. Within the control volume, we have it going like this, and then again going like this. Okay. Within the control volume, it has a different shape, but means it is divided into two parts. But from one control volume from one grid point to the next grid point, we have straight line. So now in this case, dTdx can be calculated at each phase. Okay, and kdTdx also will be correct because slope is same. So when I am solving for this grid point, I will be using the same line, and when I am solving for this grid point, I will be using the same line. So we can calculate dTdx at each phase. Okay, and heat flux will be continuous. So this profile assumption is valid. So we will be using this now. Remember our equation, k dTdx at east minus k dTdx at west plus s xc minus xw equal to 0. So we are stuck at this step. Now we will proceed. Okay, this is the same equation which is written here. I will just keep the profile assumption open here. K dTdx at east minus k dTdx at west plus s xc minus xw equal to 0. This term is already done. We know s is known, xc and xw are known. This is done. So what about this? Based on this expression, dTdx at east, okay, at this point is nothing but t at this point minus t at this point by this distance. How we have defined this distance? If you remember, this distance was delta xe. Okay. So TE minus TP by delta XC into K at this point, at this interface. So at this point, let us assume that we know what is the K at this interface. So if this entire domain, if the K remains constant, there is no issue. But if it changes from one control volume to another control volume, then we have to see how to calculate this K. Okay, but at this point, let us assume that we know what is K. So TE minus TP, these will be grid point values, so known values by delta XC, or values which we are trying to derive, stored values. Similarly, for the west grid point, KW, TP minus TW by delta XW, which is this distance, okay, plus S into delta X. Let us call this as XC minus XW, remember, it is the length of the control volume wire. We have written somewhere. This is delta X, okay, XC minus XW. So this is our approximation. Okay, KDT minus TP by delta XC minus KW, TP minus TW by delta XW plus S delta X. Now, if you rearrange the terms, we can write this as, so all the terms of TP you take to the left hand side, K by delta XC plus KW by delta XW TP, and all the other terms you take to the right hand side is equal to Ke by delta XC T plus KW by delta XW TW plus S into delta X. Okay, it's missing S into delta X equal to, no, there is no equal to, already we have used equal to here. Or this entire thing we can write as a coefficient AP. P denotes that it is the coefficient of the term TP, okay, is equal to AE, which is the coefficient of T, plus AW, which is the coefficient of TW, plus B. Okay, so APTP equal to AET plus AWTW plus B. So what these coefficients are known, okay, or can be calculated, because conductivity can be calculated or known, it is known, and delta XC, delta XW, these are already known from the initial grid generation. So AP is known, AE is known, AW is known, and B is also known. We have seen S and delta X are known. Okay. So these are known factors, okay, as I have written here. Okay. So in general, so now we have, when we have to solve, basically we have an equation of TP, the grid point value TP, in terms of its neighboring value TE and TW. For this simple case, it is similar to the finite difference equation, where also we had for ith grid point in terms of I plus 1 and I minus 1 at grid point. Same thing has happened here, but for more complicated type of control volume, it will be different. Okay. So for each control volume, we will have one equation like this. Okay. So if P is equal to 2, we will have one equation, P equal to 3. How to treat the boundary we will discuss later, but anyway, P equal to 3, 4, 5. So there will be 6 equations for 6 control volumes, which we can solve simultaneously again using our previous method or whatever. We will see later how to solve. We will go through all the different methods, but using any method, we will have 6 equations, 6 unknowns. We can simultaneously solve them to get the value of T for all the points. Okay. In general, for a 2D or a 3D problem, or any complicated shape problem like this initial shape, we can write the temperature at pth point Tp, okay, so this point APTP as all the temperature at all the neighboring points, summation A and B T and B, where A and B are the coefficient of the neighboring temperature point plus B, okay, where NB is the neighboring points. So for a regular 2D geometry, we will have 4 neighboring points. 4 neighboring points means like this: east point, west point, then north and south. Okay. In 3D, we will have 6 neighboring points: east, west, north, south, top, bottom. And it's irregular geometry. You can have any number of neighboring points. I can have 20 neighboring points also, although it's not realistic. But I can have 3 neighboring points, 5 neighboring points, whatever. Okay. So these are standard notations. You should use these notations. Do not use arbitrary A, B, C, D like this. Okay. And what we have seen, grid point value is expressed in terms of neighboring values. And once you can do this for each control volume separately, for this, you will have n number of equations for n number of unknowns, which we can solve too. We can solve using the same method which we use in finite difference. Ultimately, this discretization scheme just gives you the set of the equations, difference equation or this discretized equation. Then you, however you solve it is another thing. Okay, and we'll get the values. Any questions? Now it should be clear. Okay. So I hope it is clear because no one is asking questions. If I give an assignment, you will be able to solve. Okay. Means write a code for solving. So anyway, let us take a look at another profile assumption. Okay, so you might think that okay, I want to linear equation. We are introducing a lot of approximation because we do not know whether it's varying linearly or not. We are just approximating it. Okay, so by the way, one question is here. So we are assuming that it is linearly varying. Okay, but obviously in real life the variation might be very different. Maybe it is exponentially varying. Okay. So what will be the consequence of that? Okay, what will be the consequence? Means our final solution. What does our final solution consist of? Do we have the variations in between grid points in our final solution?
No, sir.
We do not have, right? We are just storing at the grid points. So if I divide into the domain into 100 control volumes, I have 100 values of temperature at 100 points. That's it. No variation is known. Okay, when we plot it nicely, we are basically interpolating, but that's a different thing. If you just look at the answer, it is just 100 values at 100 grid points. Okay, so basically we are just we're trying to get the values at these grid points. Okay, so ultimately, if I can get the correct values at these grid points, it does not matter whether you are using linear approximation here or quadratic or cubic or whatever. Okay, as long as you get the correct grid point values, it will be inconsequential. Whatever approximation was used, that is just a step in getting the correct solution. That is not going to influence the correct solution. Correct solution is still the correct solution. Whatever satisfies the discretized equation. Excuse me. So now let us take a look. Let us think that okay, I want to be more accurate. So instead of linear, I want to use a quadratic equation for a way like maybe it will capture the profile more accurately, or maybe cubic equation. Let us think of one case where it is piecewise quadratic, means for each grid point we are using a quadratic equation. For the wth grid point, we are using three values to find the profile. Like instead of using straight lines like this, and this is not looking like a straight line, but instead of using straight line like this, okay, from here to here, and another straight line like this from here to here, we are using 3-point values to find a profile, quadratic profile. For quadratic you need 3 points, right? For a line you need 2 points. So using the neighboring grid point of west in the west direction, which we call as WW, TWW, TW and TP, we can draw a quadratic line. Okay. So now once you have the quadratic line, obviously you can find out the derivative at W. Okay. Similarly, I can draw a quadratic line for this pth grid point based on TW, TP and T. This will be T east, right? TW, TP and T east. 10th one, right? Just a second, I will just upload the correct one. otherwise we'll forget later. Okay. So now when we are trying to find out k dt dx at waste for the pth control volume, we know what is the variation. We will have a quadratic equation basically for temperature, and then you can find out what will be dt dx at this point. Okay, it is the slope of this line. Okay. Now, will this work? Tanmay, will this work? Not there? Are you there? Will this quadratic profile work? Cannot hear you. Somebody else. Somebody else. Shivam, are you there? Will this work?
Yes, sir. Uh, Sir,
What can be possible difficulty? Remember that we are trying to get the flux, right? Heat flux has to be continuous. So if the slope of this line is different, based on this red line we are calculating the slope at this waste point for the pth grid point, right? And for this grid point also we would have calculated the flux at this interface when we are solving for this grid point. For that we are using this light blue line to calculate the flux.
Hello, sir. Am I audible?
Yes.
Sir, that line is not differentiable at grid point W.
No, it is differential. It's not, means you want to calculate at the interface. You can differentiate it at the interface. So for the period grid point, you will be able to differentiate and get the value of dt dx at this waste interface. Okay, based on the slope. Basically, it's the slope of this line at this point. But for this wth grid point, you will be calculating the slope of the blue line. So if these two slopes are not same,
yes, sir,
then the k dt dx is not continuous. So this will only work in limited cases when the two slopes are same, and that happens when these are at the centroids. Okay, these points are at the centroids. Otherwise, this will not work, and it's just more memory. You are more computational power you are wasting, and still not getting the correct solution. Okay, it will only work at the limited condition when both the slopes are equal. Okay, so to calculate this, so let me summarize this. So my point here is to show that it does not matter whether we may think that we will go with a very good approximation cubic, which we are including more points to more accurately capture the temperature, but it is actually worse. Okay, so to calculate flux at the interface W for the control volume W, the same thing is written here, just for because you will be reading this later on. The profile assumption is given by the quadratic line joining TWW, TW and TP. Similarly, to calculate the flux at the same point, at the same interface, but for the pth control volume, you are using a different profile based on TW, TP and TE. So it means that dt dx may not be equal at W for the two control volumes. Only equal if W is at the midpoint between, it will be only equal if W is at the midpoint between capital W and capital P. Okay, my initial point was wrong. So otherwise it will not be equal. Hence results may be unphysical as flux balance is not satisfied. Flux balance satisfaction is one of the important points that has to be considered later on we will see. Okay. So it means that higher order function may not give better result. Okay. There is no guarantee. Is it clear? So what we are going to do in this entire course, and even if you see when we write codes or when you write codes or if you do projects, we assume this type of piecewise linear variation between grid points. Although this is not the only method, but this is safe and works, so we do this. Okay. Any questions? So no questions. Let us continue. Stop in a couple of minutes. So what we have discussed today means what we have seen. We have discussed basically what is finite volume method, what are the steps in finite volume method, and then one of the major steps is that we have to take a profile assumption. Okay. So what we have seen is that we can take different profile assumptions, but it has to satisfy certain conditions, means it has to be physical. So different profile assumptions can be taken for different parameters that we have not discussed. But for example, for temperature, we can take a different profile assumption. For velocity, we can take a different profile assumption. Okay. Or even for the same parameter, we can take different profile assumptions for different terms. For example, for these flux terms, we are assuming that T is linearly varying. But for the source term, which may be a function of temperature, we may assume that temperature is constant. Okay. Or for different term like source term, we are assuming that source term is constant. So because that does not, what will be the correct one? Means even doing that satisfies all the physical conditions. Even if I take constant source term for each control volume, okay, because there is no need of continuity of source term in a control volume, but there is a need of continuity of flux from one to another control volume. Another point is that if Ks, this type of terms, this Ks, this we have assumed to be known terms, right? But if they are functions of temperature, then they become unknown. And then the equation becomes nonlinear, and we have to use iterative process for solving the equations. Okay, this simple solution directly is not possible to obtain. So still time is left. Let me continue. Okay. Couple of minor things. So we have seen what is discretization. We have seen finite definite discretization, finite volume discretization. And I've said that for the entire course, we will just continue finite volume discretization. Okay. So what are some important concerns regarding discretization? What are the requirements of discretization? There are two important concerns. Okay. Apart from errors and other things, whatever. One is that any discretization scheme should give us physically consistent result. Okay. And second is that overall balance should be satisfied. So what do we mean by physical consistency? Solution should be physically realistic. Okay. What is physically realistic? This example I have also given in CFD course also. It's just a repetition, but it's a very nice example to give. Say I have a problem like this: 1D heat conduction in a bar or a rod or a wire. One end is kept at 0 degrees centigrade, another end is kept at 100 degrees centigrade. Initially, the temperature is something different. Say it is 30 degrees centigrade. Okay. With time, the temperature will evolve, and ultimately, we know that the correct solution, in this case, because it's a simple problem, we know the correct solution is the linear variation from 0 to 100. Okay. If there are no source terms, this is the solution. If there are source terms, solution will be different. So now, if my solution, if I obtain a solution which goes like this, okay, if I obtain a solution which goes like this, bottom line, I have some values here, for example, which is less than 0. Okay. So if my boundary temperature itself are say 0 and 100, and there is no source term, all the values should be bounded. All the values should be between 0 and 100. Because how can it go beyond 0 and 100? What is the driving force? There is no driving force. So this means that this is not correct. This is not physically realistic at all. Okay. It cannot go beyond 0. This is unrealistic. Similarly, if it goes beyond 100, that is also unrealistic. Okay, because it is exceeding the boundary temperature. So we should have physically realistic solution. Okay. So for example, this green line, this is physically realistic, means the solution is bounded between 0 and 100, but this is not accurate. Okay, it is approximate but physically realistic. There are two different things. Sometimes students get confused here. They think that physically realistic means 100% accuracy. It's not correct. Physically realistic means it does not violate any principles of physics. So it is still correct, but it is inaccurate, means it is not exactly giving the exact profile, it is giving somewhat nearby profile. Okay. So this is may or may not be acceptable depending on how much accuracy we need. Another example of physical consistency is that insulated boundary condition. Again, I give the same example in every course. Insulated boundary condition. Okay. So insulated means there is no heat transfer across the boundary, which means that what is the heat flux? It's 0. So K dt dx equal to 0. So if K dt dx is 0, it means dt dx is 0. So T should not vary with x. So the isotherms are constant temperature lines. Okay. Right. So isotherms should be straight lines. Temperature should not vary with x direction, just near the boundary. Later it can vary, but just near the boundary it should not vary with x direction. So if we obtain solution which looks like these green lines, okay, where there is a slope here, non-zero slope here, okay, then K dt dx is not 0. So it means that it cannot be the correct solution. It's not physically consistent. So physically consistent solution should give us K dt dx to be 0 at the boundary for a adiabatic problem or insulated problem. So this is what we have discussed. Dt dx equal to 0. The isotherm should be perpendicular to the wall. So this is one way we check whether the code is, when we write a program or a code, whether the code is working correctly. We give a simple problem to solve, and then we see, like an adiabatic problem, we see whether we are getting this, satisfying this condition or not. Okay. So this is one thing, one point. And second point is, so physical consistency we understood. Overall balance. So physical consistency, any like it need not be only in terms of temperature. So it can be anything. Okay. We have to check whether the result is physically correct or not. Means it is acceptable within the governing physics. Okay. It should not be beyond what physics predicts. Okay. Like for example, I give a cooling to a metallic sphere. I drop a metallic sphere of 1000 degrees centigrade into liquid water at 30 degrees centigrade. And I have written a program, and my program says that the temperature of the metallic sphere is increasing from 1000 to 1500 to 2000. Obviously, it is physically inconsistent. It cannot happen. Temperature should decrease. It may not give the correct decrease rate, but it should decrease. And second point is overall balance. Overall balance we already discussed that any property should be balanced. Property means mass, momentum, energy. This should be conserved over the entire domain. Okay. So even if you use finite difference method, which does not guarantee that conservation, we have to check whether our answers are gives conserved results or not. Otherwise, we have to modify. Okay. Conservation should be valid over the entire domain. Heat flux, mass flux, momentum flux, etc. must give overall balance with appropriate sources and sinks. Okay. Conservation should be valid for any number of grid points. Even if I have only 3 grid points or 5 grid points, very close grid points, still this property should be conserved. Okay. It should not be that only if I have infinite number of grid points, it becomes conserved. Infinite number of grid points, anyway, it becomes conserved because you are reducing the finite, you are reducing the discretized equation to the actual PDE by taking infinite number of points. So it will become conserved. But for coarse grids also, it should be conserved. And this is where the main advantage of finite volume method comes. Inherently, it makes it, so we don't have to worry about it. Inherently, the variables will be conserved. Okay. Only thing is that care is needed to calculate the flux at the control volume interfaces. We have discussed this in detail today. That profile assumption should be such that the flux is continuous at the interfaces. Okay. Let us stop here today, and we will continue this finite volume method discussion, some other points in the next class. Any questions? Let us stop the recording.